So before we move on to the last 4 log identities, let's recap last lesson's 5 identities. So the first one is log base of b, where the argument position is also b. So in this format, what we're asking for is b to the power of, so b to the power of what will give you b, and in this case, b to the power of 1. All right, so the idea is whenever the base and the exponent, the base and the argument are the same, the resulting answer will be 1. The next one is going to be part number 2, where we have same format, but now we have 1. So the question right now is b to the power of what will give you 1? And from last lesson, we know b to the power of 0. Anything to the power of 0 is 1. Third one is what happens if you have the base is b, but the argument format is in an exponent form, b to the n. So the question right now is b to the power of what will give you b to the power of n, and in this case it's just going to be n. The fourth one is a modification of the third one where you have the base, you have the argument, but each format is going to be in an exponent form. So over here it's m. So what we found out in last lesson is we take the ratios. So if the bases are the same in the argument position and the base position, the resultant value will be the ratios of the exponents. In this case, it's going to be n over m. And the last one is a bit of a, so these 4 are pretty much kind of the same format, same format. The last one is a little bit different, the fifth one. It's when the overall format is a exponent form. So as you can see in this format, this is the base and this is the exponent, and the exponent is a little bit more complicated because there's a log in the exponent. And what we found out last lesson was when you simplify this, so when the bases are the same, the base of the exponent and the base of the log expression is the same, the ending result is the argument. So now we move on to the 6th log identity, which is called the sum. Because in this format here, what we can see is here that if you have 2 logs with the same base, what happens when you add the log expressions? What is going to happen? So we're going to actually prove this. So in each case, I'm going to let each piece be equal to another variable. In other words, I'm going to let the first one be x. So let x be log bm. And this one here, let y be log bn. So if you notice, we have log form. And what we're going to do next is change each of these formats into a exponent form, because all log formats can be converted into a base format. So recap from last lesson, to change this into log format, we have the argument position m is equals to the base to the power of the exponent. Same thing for here. We have the base, or we have the argument, which is n, is equals to base to the y. So what we're going to do right now is take these 2 and multiply them together. So what happens is I'm going to take m times n, so we have m, n, and what we're going to do is we know that m is equals to b to the x, and this is b to the y, okay? And the reason why I'm multiplying is because in this part here, we're going to see that when we multiply same bases back in grade 9 exponent laws, you add the exponents. So in other words, we have a sum happening in the exponent form. So when you have bases multiplied that are the same, you're going to have x plus y. And if you notice this format is actually an exponent form, where you have the b is exponent, we have a binomial in the exponent part, b is the base, and x plus y is exponent form, and this whole thing is your answer or the argument. So but now we have exponent form, we can change it into a logarithmic form. So remember what log form is? You take the exponent over here, call it x plus y equals to log base of b and m of n. So these 2 formats are the same. So I'm going to put my over here, we have x plus y is equals to log mn. So now we notice how we have a sum going on here because this identity is called the sum of logs. And the question right now is, what's x? What is really x? So x is this part here, which is log bm. So we have log bm plus, and what's y? Y is log bn is equals to the right hand side, which is log mn. So right here we have the sum of the log identities. What this means is, all right, if you look at the left hand side, we end up with the original question. But to simplify this, if you notice what's happening, oops, I left out a b over here, there should be b over here, is when you add bases of logs that are the same, all you have to do to simplify is take the product or multiply the argument. So if I were to take an example, log 2, 5 plus log 2, 7. So in this case, we can simplify this. They have the same bases, so we can actually add the logs together. And what happens is, to simplify this, we just take the arguments of each log expression and multiply them, 35. So what this is called is a single logarithmic expression. So now let's move on to the seventh one, which is called the difference of log identities. The way we're going to prove this is exactly the same thing as the one previous before, is you're going to let each piece be a variable. Let's call it log bm. We'll call this y is equals to log bn. We're going to change each of the log formats into exponent form. So you have m is equals to b to the x, n is equals to b to the y. And we're going to take these m and n, instead of multiplying them, we're going to divide them. When I divide, all right, what happens is I have m is b to the x, and this is b to the y. And what we're going to have is, what happens when you divide expressions that have same bases? What happens to the exponents? They're going to be subtracted. In other words, we have bx minus y. And this is the beginning of the difference of log identities. Now, this format is actually in a base exponent argument form. We're going to convert this back to a log form. In other words, we end up getting x minus y, which the exponent is equals to log, the base is b, and this argument part belongs in the argument part of the log form. So over here, the right-hand side, I'm just going to rewrite this out again, log base b m over n, and we end up getting x minus y. X minus y, we go back to what we called x. X is actually log bm minus y is actually log b n is equals to log bm over n. So what the statement is saying is that if you're to subtract log expressions with the same bases, to simplify this, all you have to do is take the ratio or the quotient or divide the arguments m over n. So let's do an example. If I had log base of 2 argument 25 minus subtracting log base 2, 5. If we're to simplify this, we just take the same base, but we take the argument. We're not going to subtract the arguments based on this expression identity here. We're going to take the quotient. You take 25 divided by 5, which equals to log 2, 5. And just to further on the sum and difference, you can only subtract and add expressions when the bases are the same. If I change this 2 to a 6, you cannot use the difference or the sum. The bases have to be the same. So the 8th rule is called the power rule. This is a very popular one that we'll be using when you solve exponential equations. So here we have a log form. You got the base, the exponent. Over here you got the base, the exponent form, and the argument. And we're going to convert this back to exponent form. So let's let b to the x is equals to a. Okay? But the power rule says, power rule means you're going to actually add a power to both sides. In other words, I'm going to make it to the power of n on one side and the power to n on the other side. And as you notice, this is still exponential form. But which side would you want to isolate? So in this case, we're going to actually let this part here be the exponent. This is your base, and this whole thing is your argument. So in other words, we're going to have something that looks like this, but a bit modified. So over here, to change this back into log form, we're going to have log b, the argument, with the exponent part, and we end up getting x to the n, because this is the exponent part, okay? And if we go back to what x is, what is x really? X is actually this piece here. In other words, log b a n is equals to, I'm going to switch it around. I'm going to put the n in front and replace the x with the log b a. And you might think, what's the big deal with this? So what I'm trying to say right now is, based on this format, if your argument is in an exponent form, what we can do is extract the n and rewrite it outside as a coefficient. What I'm trying to say right now is, if you have log, for example, 3 to the power of 4, so where this is your argument and this is your base, what we can do with the 4 is we can actually make it a coefficient of the log expression with the same base. So now we come to the last log identity called changing bases. And if you remember the 6th and the 7th identity where you add things with same bases, well, what happens if the bases are different? Well, we can't add them or subtract them, but we can actually do something to it using this 9th identity to actually add and subtract expressions that have different bases. So we're going to change the base. So now, if you recall this, log 100, if I were to ask you to evaluate this, give me a number using your calculator or not a calculator. Well, keep in mind that if there is no base, it's automatically a base of 10, okay? In other words, I'm asking you 10 to the power of what will give you 100. In this case, it's 2. Or all your calculators should have a log button that looks like this. What that means is log base 10, which everyone has. Now for this one over here to the right, log base 300, not everyone has a button that looks like this, where you have an option to insert whatever you want for the base. So this is where we're going to have to use a technique called changing bases. So if you have this button, that's great, but if you don't have this button, then what are you going to do? So we're going to call this equals to x because we're looking for that number. We're looking for x, okay? So we're going to change this back into exponent form. This is a log form, so we have 3 to the power of x equals to 100. So this is actually an exponential equation, okay? And we're solving for x. Now a technique is we're going to treat both sides the same. I can multiply everything by 2 on both sides. I can take a certain function on both sides. And in this case, I'm going to take the log of both sides. What I'm going to do is insert log base 10 and log base 10. And the reason why I'm using log base 10 is because my calculator has a base 10. And you're wondering, okay, this is getting more complicated. There's a technique we learned previously, the power law. If you look at the left-hand side, right over here, notice how you have the base of 10, but your argument has a exponent form. What we can do with this x is remove it on the outside, relocate it. I shouldn't call it remove it. So in other words, we have x log base of 10 is equals to 3 is equals to log base 10, 100. And we know that on our calculators, you can actually get the number for log 3 base 10 and log 100 base 10. In other words, I'm going to isolate for x because keep in mind we're looking for x. In other words, we have log base 10, 100 over log base 10 of 3. And if you put this in your calculators, you end up getting the following. 4.19. If you had that special calculator button, this one up here, you would get 4.19. So what we did with this expression is we actually took the 3 and the 3 and changed it to a different expression, base 10, because we have log 10 base 10 button on our calculator, to actually give us 4.19. In other words, if I were to take log 300, so special calculator people will get 4.19, or those without that special calculator button can still get this 4.19, but you just have to change your base. So notice the expression over here. We can actually take the 100 numerator, the base of the log denominator, but the base is what you want. You choose the base. You would choose base 10. But miss, do I have to use base 10? You can use it whatever base that you want. Okay, so what I'm trying to say right now is changing bases, general format is the following. I'll call this log base of b and call it a. All right. What we can do is changing bases looks like this. You have log, argument numerator, base denominator, and I'll put a little c here. C is going to be any number that you want to be as long as it's greater than 0 and it's not equal to 1. To whatever number that you want that satisfies this condition. So what I'm trying to say is log 300 is equals to log 100 over log 3, and I could put, for example, put 7. That would be one possibility. I can call this 6. I can call it 1,000, whatever I want it to be. So we use changing bases when we solve exponential equations. So I'll use blue here, okay? So let's just say you had, for example, 2 to the power of x is equals to 7, okay? In this case, you got a couple of ways to solve for this. Some students with a special calculator can go directly into log form, where you have x is equals to log base 2, 7, okay? Or If you have this format but don't have that special calculator, this button here, you can change bases to log 7 divided by log 2. I don't have to put the 10 here because it's automatically default 10. We also change bases when we have an expression like this, where the bases are different and you can't do anything with it for now. So let's look at the first one here. Well, the reason why I can keep on going is because the bases are the same and we're adding. So this is the sum log identity. In other words, we get log base of 2, and then we're going to take the arguments of each piece and multiply them. All right, so you get 90. But you can't do the same thing for here because if you notice here, the bases are different from each other. However, there's something going on with, there actually is something connecting 2 and 4. Well, we know that 4 can be rewritten as 2 to the power of 2. So there's something going on with 2 and 4. So what we're going to do is change bases. The fact that 4 can be expressed, so if 4 can be expressed with a base of 2, this tells me that I should change everything to a base of 2. So when I say changing bases, this one here, well, I don't need to change it to a base of 2. It's already to a base of 2. But this one here, going back to the last identity that we just did, we're going to rewrite this out as log 10 over log 4. But instead of having nothing in the base, which is automatically default 10, I'm going to choose specifically 2. And the reason why I'm choosing specifically 2 is because 2 and 4, these 2 and 4 are connected with 2. Okay? And you might think this is a bit more complicated. It's getting more bigger, especially the right-hand side. But keep in mind, you can actually simplify certain things. So over here, one of the identities, the first 5 identities we did was the following. So if you look at the bottom part, all right, this 4 can be written as 2 to the power of 2. And if you remember one of the log identities, b to the n is equals to n. So in other words, the denominator actually becomes log 2, 10. This actually becomes 2, okay? 2. And this is just still a 10. All right, so it's getting simpler. And if you notice on both hand sides, they both have an expression that have base 2 and base 2. But unfortunately, you cannot add these two directly. So this kind of looks like this one up here, all right? You cannot take the 9 and 10 and multiply them. Why is that? Because we have a coefficient. We have a number here, over here. This 2 is in the way, okay? So what we're going to do is, I'm going to rewrite this out so you can see the format of this. So divided by 2 is the same thing as 1/2 log base 2 and 10. And because of the half in front, we cannot multiply the 9 and the 10. We cannot add them directly. But what we can do is, using the power, remember how the power law says the coefficient can be brought in a different format? So what this becomes is the following. Log base 2 9 plus log 2 10, but now this half becomes an exponent right over here. And now we are in a position to use the sum log identity because there is no coefficients. So now we have base 2, argument, no coefficients. Now we can use the sum identity. So when we use the sum identity, you just take the 2 and multiply them together. Okay? And if I didn't want to have that half, that's the same thing as 9 root 10. And this is the simplified version. But we had to go through a lot of log identities. We had to change bases. We had to use the power rule, and then we had to add them at the end. So this next example is pretty much the same thing as before, but you might think 0.5 and 2. What is the connection between 0.5 and 2? Well, 0.5 can be rewritten as 0.5, 1 over 2, and 1 over 2 can be written as 2 to the negative 1. So in other words, 0.5 is related to 2 directly, base 2. So in other words, I'm going to change everything to a base of 2. So over here, I get log 9 base 2, log 2 base, I'll put 1 over 2, minus log 2 10, and pretty much everything's the same as before. Now we're going to have to clean this up, all right, as in simplify this. And because we know that 2 to the power of what will give you half, all right, that becomes negative 1, okay? Because this can be rewritten as 2 to the power of negative 1, and going back to one of the log identities, base, you take the negative 1, okay? And now this negative 1, we're just going to put it in front of the log base 2 9, okay, and over here. And this is where you subtract, but you got to be careful because subtraction, you cannot have any coefficients in front. This cannot happen, okay? You got a couple of options here. What you can do is factor the negative one out if you wanted to, all right? If you factor it out, you end up getting negative and the sum. Or if you really want to deal with a negative one here, you can use the power rule and bring it inside. So there's a couple of options. So I'll show you one. I'm gonna factor the negative out. So I have log 2.9 plus log 2.10. The negative stays outside, and now we have a sum. In other words, we have log base 2n 90. So that's one possible answer. Another alternative is if you want to deal with a negative one and bring it using the power law, you can. You have log 2, 9 to the power of negative 1. So this is a negative 1 outside. We can put it into the exponent on the argument, minus log 210. And if you notice, these two are the same. The bases are the same, so now we can subtract them. Now, if you subtract bases that are the same for logs, you're going to have to take these two and divide them. In other words, you have 9 to the negative 1 divided by 10. And if we do that, we end up getting, if I just simplify this, 1 over 9 divided by 10, which is log 2, 1 over 90. Okay? And these two, they look different. They do look different, but they're actually the same. Because I can take this one here if I really wanted to and rewrite this out as a exponent form, a reciprocal form, and this negative one can be written on the outside, which will end up with this. So what I'm trying to say is when you express a simplified version of a log question, there's many different formats. But both of these formats is called a single log format because you only see one log and you see the base exponent. Single log, base exponent.